Hello everyone, welcome to part 2 of this two-part series. The plan is I'll give you a complete walkthrough of the Voronoi edges algorithm. After that, I'll show you how I made this. By the way, this algorithm is based on the original Voronoi edges algorithm by Inigo Quilez and one of the faster variants by tomkh on shadertoy. The Voronoi edges pattern depends generally on 4 things: having positions of points, finding the closest point to our pixel, testing nearby points for edge distances, and shading pixels based on the closest edge distance found. A naive example might look like this. You have positions and your point A, then you get your distances of edges generated between points A and each of the other positions. You find the smallest distance and use that to shade the current pixel. The only real difference between this code and the naive Voronoi algorithm I showed in part 1 is how we get our distance. Understanding this one function is 95% of the Voronoi edges algorithm in my opinion, so let's jump in. Let's say we have 2 points A and B. We can find the halfway point easily, and I'll show you that soon. Then the easiest edge to try and make is the one that is halfway between A and B, and that is exactly perpendicular. And if this whole program is running for a given pixel, we have that pixel's UV coordinate, and in fact we can create a vector going from the halfway point out to that UV, and I'll show you how to do that soon as well. So on paper we can work out that the closest distance to the green edge would be a line like this. The problem is we don't have any real reference to this edge yet, so we can't find a distance, so we need to explore the situation and see how else we can describe things mathematically. What we can find is we can see that with this UV vector and that AB line, we can kind of make a right angle triangle if we fill in that missing side. And that also gives us a distance to the halfway point, which is on the edge line too, and would be the same distance as the one we're really looking for because they're parallel. So how can we make that right angle triangle and find the distance to the halfway point? The answer is the dot product. It will make a projection of A on B, and as long as the B vector in this diagram is normalized, the length will be that exact projected length, A cos theta, which is the one we need. And then we'll get our answer. As long as that makes sense to you in theory, we can move on to answering these important questions. How do we get the halfway point? How do we get a vector from halfway to UV? And what vector do we project that onto? So here we're finding the halfway vector. If we have our point A and B and the halfway point between them, and A and B are actually vectors coming from origin, then we can show these vectors added tip to tail like this, giving us a new vector from 0 to wherever that new endpoint would be, and it crosses the halfway point at halfway. So if we multiply that vector by 0.5, we get the green vector to the halfway point. Slightly out of order, but the vector we project onto will be a unit vector along B to A. If instead of adding A to B, we subtract B from A, and then we line B tip to tail but flip the other way to show a subtraction, then the resulting difference vector in white has the same length and direction as going from B to A. Next, we normalize that to get our unit vector. So that gives us a direction vector something like this. So we have the halfway point, we have the direction vector, and we're just about ready to calculate this last line. We subtract halfway from UV to get a vector that can be seen as going from the halfway point to the UV. Now we have the direction vector and the halfway to UV vector. They're really both from origin out, but they still hold all the relationships we need to find the distance to that green edge without actually being positioned there. So we whip out the dot product and return the result. Here's a quick animation of that function applied on just 2 points. The point A, which doesn't move, is in red, and our point B is in green. The gradient goes to black beyond the halfway point, where the dot product returns negative distances. After hearing all this, you might suspect that you could do a similar function in 3D to get the distance field for a plane. Here's a quick shader I wrote just to bring that idea to life. The points are modeled here as spheres. Point A is the red one, point B is the blue one, and I've added a grid texture on the plane just to make it fancy. It really is just as easy as using vector 3s instead of vector 2s in this edge function, although in 3 dimensions you would need a ray marcher to get that distance. This isn't the way you would actually usually go about getting the distance to a plane though. The point is, the whole Voronoi edges algorithm can also work in 3D. Okay, it's time for code. Here's the first half of the code for the Voronoi edges algorithm. As you can see, it's almost identical to the basic Voronoi function with only one real difference. We store the position vector for the closest point so that we have it in the second half of the function. Here's the second half of the function. As you can see, it also repeats a lot from the first half because we need to check all the neighbors again. So we set up a minimum distance. I'm using a second variable just for clarity. This part of the function is exactly the same as part 2, so I'll fade it out a bit so we can focus on what's different. The position we get each time through this second double for loop is stored as b. We're using the dot product of a and b twice as a cheap length calculation. What we're really asking is, are a and b the same vector? We have to check this because at some point they will be the same because we're producing the same 9 positions as earlier. If a and b are the same, we'll use continue to skip the rest of this round. Now you might ask, why don't we just use equals equals? The reason is because floating point numbers have limited precision. Vectors a and b could end up not being exactly the same, even though logically they should be, so this lets us get around that. I bet you can recognize those next 3 lines now. That's everything we've been talking about, so we just let it do its job. And we store the result in dist to edge, which we compare with any other distance we've already seen and keep the smaller one, just like with the basic Voronoi distance. At the end of the whole process, we return that minimum distance, and we call it in main here. So if every pixel does that, we get our edges or edge gradients, and this is the result. Before we get on to the art, I just thought I'd mention, you will find other versions out there that to me seemed a bit harder to understand. For example, a lot of them use UV minus position or position minus UV for their point A and point B's. Algebraically though, the result is still the same. For example, with B minus A, if we substitute that with our UV position, we get this. The UVs just cancel out and the A and B even swap sign, so it's exactly what we have. The same thing happens here for our length calculation. And here, after substitution, we can collect the UVs and say to UV, we can distribute the 0.5, giving us just UV, and 0.5 times position A minus 0.5 times position B, and we can pull out a negative 0.5, and then it's the same as what we have again. Are you ready to see an application of this algorithm as an art piece? Here's a list of the additional techniques we can use to create an artistic Voronoi pattern. Just a disclaimer, some of these are slightly hack jobs or complete hack jobs. So for smoothing, Voronoi edges give us sharp geometric corners which can look great, but we can also make things smooth. This is a function that takes in 2 functions or values and a third scaling factor, and instead of returning the minimum, it returns the smooth minimum. That means if 2 edges are forming a sharp corner, this would smoothen out that corner. I'll leave a link in the description for a resource on this. We replace the min function in that second min distance calculation with our smooth min. We also pass 0.1 or 0.2 as the smoothing factor. Larger smoothing factors mean more smoothing, but possibly more artifacts and other issues. Here's a result which looks much more organic. A sine wave is an easy way to make an organic animation because it's naturally smooth. We can pass the 2D offset vector into the sine wave along with adding the time uniform. This means both components of the offset vector will have the same time added to it each frame, and both components will go through the sine function. The result will be a 2D offset vector with components between -1 and 1 that change over time. We transform that range to be between 0 and 0.6 so the cells don't move too far away, which would ruin the effect. We need to do the same calculation in both halves of the algorithm where we do our loop to get the offset vector. That makes sure the positions we find at neighbors in the first half are the same as in the second. And the result is a smooth organic movement. If you wanted the movement length to be longer, like for example from 0 to 1.6, then you might need to check a larger radius in both loop blocks to accurately find the closest point. If this line represents the possible distances for our Voronoi edges algorithm, they go from 0 to 1. We want to make a border by flipping part of it high again. So first let's subtract a bit from the whole thing so that it goes a bit negative. Then we use the absolute value to flip the negative to positive, and the borders will be from 0 to 0.1, and the border of another cell will join with it and give this effect. That's what the code would look like, and this is the result. I actually used this border calculation instead, although I arrived at it kind of randomly. I already coded this, so I know we'll need more information from our Voronoi function for border coloring and texturing. Let's get that info now. This first variable is border, which we already created. We'll also need the border free distance, which is our original second min distance. We will smooth step it where the borders would start, and we'll use that as a mask for coloring later. If we just return UV here, at best the texture would look a bit flat, but at worst there would be either repetition or sharp cutoffs, discontinuities. We can take advantage of the fact that our A position and all of the UVs are global positions, and create new vectors that go from A to any UV. That way, when we call the texture with these vectors, we get something that better fits the shape of the Voronoi cells. We do that by just subtracting A from UV or UV from A, and we'll come back to this soon. Also, we need to make this a vec4. Now we just have to make changes based on what we return from that function. We can store it in a variable like data to use parts of it for other things going forward. We want to use lighting as if the scene were 3D, so we need to create information about the surface's curvature. The normal is a way of describing the curvature with a single vector. Normals are generally thought of as three-dimensional vectors coming out of a surface exactly perpendicular to the plane of the surface at a given point. We want to build this normal component by finding differences in distance to the surface along each axis. Just to give you a bit of intuition if you've never seen this before, you might remember calculating the slope between 2 points on a function. You get the value at f of x, then you get the value at f of x2, you take their differences and that's your rise. You take the difference between the x and the x2 that you use to get your rise, and then that gives you your run. Rise over run is the slope. Later you learn that if x2 is as close as possible to x1, you get the slope at x1 specifically, which is the start of calculus. That was just one dimension. We can do the same thing in 3 dimensions based on distances away from the object as we compare along x, along y, and along z. If we bundle all 3 of these slopes into a 3D vector, that gives us a way of describing the curvature of the surface in all 3 directions, and that's the general idea here. This technique is called central differences, or the central difference method, or central difference formula. It's based on the finite difference method, which is a foundational concept in calculus. This is a 3-dimensional version of the normal function. There are many different, more efficient versions of this code. This is just the easiest way to understand it. Because this is a 2D scene, it's really as if we're staring down the z-axis directly all the time. That means our z component will be fixed as epsilon, or 2 epsilon more general. In an actual scene, the function would look something like this, and I just put it in the main image somewhere after I returned our data. And we'll need to make this change to grab just the border value from the return vector, since it's a vector 4. And to see what the normal looks like, we can set the color to equal the normal directly. What we might find is the normal is the opposite of what the borders show. This is because when we see the borders, we see brighter spots as being closer. The normal calculation, though, sees bright spots as distance values, making them larger, making it further away. So if we wanted to flip this, we could subtract each of the map function calls from 1, or we can just swap the signs of the 2 function calls so that we subtract the right from the left instead of the left from the right. Now that we have the normal, we can add some other necessary ingredients for a scene: lights and camera. Our camera is called RD, which is short for ray direction. It represents a ray into the screen for each pixel, and the direction of the ray is slightly different for each pixel. And that allows every pixel to pick up its own small sample of the image to paint itself with. The Z value will be -1, meaning we're saying -Z is the direction we're looking into the scene, which means Z is the axis the Voronoi height map will vary on. For lights, we create 2 light position vectors and 2 light direction vectors. The direction vectors create a surface position by using the UV as the x and y of the surface position, and the border distance from data.x as the z of the surface. By subtracting the surface position from the light position and normalizing, we get a light direction vector. Now we're ready to model diffuse and specular lighting, which are borrowed from the Phong reflection model. Diffuse lighting happens when the light hits a rough surface like concrete. The light bounces off in different directions, so you get a sort of faint light. Where the normal and the light are the most in line will be brighter, and where they're out of line will be darker. So in code, we take the dot product of the light direction and the normal, we take the max of the result, and 0 since the negative numbers could affect our final color otherwise. To understand specular lighting, let's say we're in the apple section of a grocery store and there's a light overhead shining down on the apples. On this apple, we can see where more light bounces off of it and more or less directly into our eyes. Those spots are brighter and closer to the actual light's color, which I assume is white here. GLSL comes with a handy function called reflect, which does exactly what it says. It means that if our incoming vector is flipped to point into the surface, the reflected vector will go out from the surface again. Once we have this, we can reflect the light ray off of the apple's normal at a point, and then for every point on the surface, we can get the outgoing reflected ray, and we can find out how much that reflected ray is in line with our eyes. So what we need to do is flip the sign of the light direction by adding negative so it points in, then we reflect that vector against the normal to get the outgoing reflected ray. We also flip the sign of our camera ray so that it points to us. So if we take the dot product of the reflected ray and the flipped camera ray, we get the amount of light that is in line with our view. So we do that here, and again we take the max of the result and 0 to clip off negative numbers. Then we use the power function to increase the intensity of the light. The lights are applied by adding them to the color. I scale down the diffuse to 0.3 and the specular to 0.8. I also give each specular light a specific color by multiplying it by the color. Just a side note, but in the final code of my shader, the negative ray direction is just ray direction. It's wrong, but I didn't catch it before building all of the art and coloring around it. Let's give the object its own color using this fancy color palette technique by Inigo Quilez. This palette takes advantage of the periodic nature of cosine waves. We can input a vector 3 into the cosine function as a coloring offset along with an input value. Here we'll use uv.x as the input, which will spread the color palette across our screen. Let's use the x component of the Voronoi edges data variable as the input to this function. We'll use the result as the base color for the Voronoi edges cells. And this part of the code, the thing that makes the borders pop, is really hacked together. I put 2 versions here. The uncommented one is slightly more understandable. After getting that hacked border color, I mixed that color into the original color based on data y, which is the original edge distance, but smooth stepped to get just the borders. So our data variable z and w components hold this vector that we made, uv minus a. We can use it like this to get our texture value and mix it into the color based on the original edges distances. I just took it a small step further by subtracting that vector from the screen UV and dividing everything by 1 plus data x, which is the bordered Voronoi gradient. That makes this a little bit more warped. And I'm accessing the organic 4 shadertoy texture. Shadertoy comes with 6 cube maps. Cube mapping is used to simulate distance environments or reflections. This is what a cube map looks like if it's unrolled or unwrapped. Each of these 6 squares would be applied to a face on a virtual cube surrounding our scene. When a camera ray shoots into the world and hits an object, the ray is reflected and the new vector direction will point to a pixel on a face of the cube. We use that value as the reflection on our object where we hit it. We use the same texture function, but now because iChannel0 uses a cube map, it accepts a vector 3. So we give it the output of that reflection of our incoming vector off of the surface normal. Then I mix the value we found from the cube map based on if we are on a border or not, so the border can be more glossy or metallic looking. I hope you got a lot out of this video. Feel free to leave any questions, feedback, or suggestions for future videos in the comments. I'll see you in the next one.